Okay. Hello, everyone. Welcome to RubyKaigi. Congrats to release Splatoon 3. So I'm super happy to be here in RubyKaigi again. My name is Uchio KONDO. I work as an infrastructure engineer at Mirative, a Japanese startup, which provides live streaming for mobile devices. I'm here today to talk about BPF. However, in the first place, most people probably don't know what BPF is. So to catch your attention at first, I have prepared an easy-to-understand demonstration. Okay, have you read the Cloudflare's blog post about how Linux handles packets? In it, they talk about how connections accumulate in a queue in the kernel every time the server accepts the connection. So here we have two environments to experiment with the same Ruby server and the same configuration. However, there is one parameter that is different. The kernel parameter net.core.somaxcon. It is set to 4,000 for one and 500 for the other. Then this is the result of the experiment. With somaxcon is 500. The response time is clearly more erratic than when it is 4,000. It can be assumed that this is due to queue saturation. So now, I wrote some short Ruby code and a little bit C code to create a tool. So using this tool, we can visualize the current capacity and max capacity of the accept queue in the kernel. I'm going to show the demo. Now running a tool showing backlogs, and then running Apache Bench, then visualizing queue size and queue max size. So this tool is purely written in Ruby and a bit C. So using Ruby, we can visualize the server status. So, okay, this is BPF. Thank you. So keep it going. Now, I'm going to have a quick introduction to BPF. But you know BPF is somewhat complicated. Therefore, I have prepared an overall diagram. So please look at it in detail later. But I'm going to describe the short version of information about BPF. So the first theme is history. BPF, the Berkeley packet filter was first introduced to the public by a 1922 paper. It was then incorporated into several operating systems, and it was introduced into Linux in 1997, where it is called classic BPF. Then significant changes were made in BPF in 2014. Since then, BPF is called extended BPF, and then the usage scenarios have been increased. And in addition, various features required by the container ecosystem have been added to BPF now. So then I'm going to describe how it works. But there are many documents about BPF. So today, just remember simple instructions today. BPF programs are first created from script or C source code into a binary. Then this will be loaded into the kernel by a BPF system call. Then they are executed in its BPF VM. And the results or collected data are retrieved into user LAN via a storage called BPF map or some other pipes. So what we should remember is that code and data are exchanged between the user LAN and the kernel world. So running kernel program and then get back to user LAN. Also, today I won't discuss about the technologies called BTF or BPF core. These require specially configured kernel and are not yet considered widely usable, I think. Okay, now it is time to compare with other tools. There are several tools that provide functionalities similar to BPF, but today I focus on two tools. For example, do you know strace? Strace provides powerful tracing of system calls, but it has a large performance impact because it repeats stopping and resuming the process. So the performance can't be ignored. Next tool is perf. Perf is very useful to find the function that is a bottleneck in a program or whole system. However, remember that it should be only a sampling, but BPF can trace every call of functions. So BPF has some strong points from other existing tools. So let's look into its use cases. BPF are now used many aspects of systems, such as original packet filtering, advanced networking configuration, kernel modules, such as LSM, cgroup, and more. Typical OSs using BPF are, for example, Cydium and Falco. Cydium provides network orchestration for containers using BPF. Falco provides threat detection and other security features. These are very widely used by cloud-native applications. Other interesting tool is RbPerf, it is created by Javier H. Koto. This tool is to observe Ruby's performance and debug. Okay, then RbBCC is also made mainly for observations. Okay. So what is RbBC? In a short words, it's BCC for Ruby. Then, what is BCC? Yeah, BCC now stands for BPF compiler collection. It is so-called an SDK to make BPF tools using script languages. BCC officially supports Python and Lua, but they don't support Ruby. So I created RbBCC to use Ruby to control libBCC's features. So, I'm going to show how to use RbBCC. Then it describes how to use BPF. Okay, there are. BCC has important 4 key probes to be used as a data source. First one is kprobe. Kprobe is used to trace functions defined in Linux kernel. For example, this archsys execve this is the substantial function called in kernel when execve syscall is invoked. This short Ruby code is the example to use RbBCC with to trace sysexecve calling. In writing RbBCC code, there is a C part in it. This part now defines the function called every time specific. The function called when every time specific kernel function is invoked. And in it, function in this example, when the func is called, the counter is incremented. The Ruby part first loads this C code above, and then gets feedback from BPF program inside kernel. In this code, first attaching the kernel function, and then making a loop, get sleep 3 seconds, and get the kernel data from BPF map, and show and clear, and repeat again. This is an example working demo. Oh, okay. Sample RB is running. Then run a simple program. The counter is incremented. 3 times invoking and 3 times incremented. Running many times Ruby program, and then counter is highly incremented. So the first demo used the TCP v4 con request function in kernel. And so real world BCC code is such big, but it includes both C code and Ruby code. This tool makes these types of output. So this is the first key for tracing. Next one is tracepoint. Note that this is different from Ruby tracepoint class. This is Linux kernel tracepoint. It is a static entry point to trace kernel events, and it won't change its spec in the future. Kprobe, on the other hand, traces an exported symbol of kernel. It should be changed and maybe unstable. Zero, zero trace points that is invoked when every system call is invoked, and every system calls are returned. Raw syscalls sysenter and raw syscalls sysexit. I used these trace points to mimic the strace behavior using BPF. This is my handmade strace demo. Network is a bit slow. Sorry. Okay. Now tracing system calls shows what system call is called and how many times elapsed. Also compare the real straces output. For your information, I want to show about the performance side effect by tracer. Here are parameters to experiment, and both Ruby and strace return the same output, right? But when strace is tracing some program, the performance gets somewhat deteriorated, but BPF makes much less deterioration. It can be used for live processes or production applications with this negative effect. So, third key probe is uprobe. It is a mechanism to attach to user space programs, function calls. It's like kprobe, but it is for our programs. Okay, by the way, in this slide, I'm going to use Ruby and trace the Ruby, but the Ruby binary is built with specific configuration options, enable dtrace and disable shared. So let's trace some Ruby functions. The example case is RbStrNew. This is namely called when inside Ruby a string is created. Okay, this is Japanese description of RbSTL new. So we are I'm going to collect this function's return timestamp and entry timestamp, then doing the subtraction. The delta of function, the delta of 2 point represents the latency of a function call, right? So there are two probes named uprobe to trace function entry and uret probe to trace return. There are also kprobe and kret probe. Okay, then this is the example output of RbSTL news latency in a histogram. So last one is USDT, user space statically defined trace point. USDT is for uprobe, just as trace point is for kprobe. And in the Ruby has some USDT definitions and it is documented. So please refer to it later. There are some USDTs about ZC in Ruby. ZC mark begin, ZC mark end, ZC sweep begin, and ZC sweep end. So maybe they can be used to trace ZC latency, right? So I created a tool to trace Ruby's resident set size memory, and ZC invocation count, and elapsed time. And this is the part of the tool's code. So I tried this tool for some Sinatra web application. And I made the intentedly ramping up this Sinatra. This is working demo. So sorry. Koi. So I'll show this demo later, but this visualizes RSS, mark elapsed time, and sweep elapsed time. When the program was ramped up, the mark phase took longer time. We can visualize this using BPF and USDT. So, summary for now, I have introduced 4 probes to be used by RbBCC with some examples. Two important things to remember is that we can use Ruby to trace Ruby. So next theme is observability in action. I'm going to show real-world tuning. For example, I created a sample JSON parser gem and named it Ruston because it's written with Rust. But it's naively implemented first and somewhat slow. This is the demo benchmarking code. 50,000 times invoke the parse. The result is clearly slow. So I'm going to improve my Ruston code. Then, what command to be invoked first? It is perf. I run perf and get some bottlenecks. Perf is very useful to grasp the overall bottleneck. This is CJSON's frame graph. This is Ruston's first frame graph. There are some differences in its graph. Maybe we must look into these functions. So let's start tracing by BPF. At first, I focused realloc and free invocation counts. Wrote some tool in RbBCC. So there are significant differences. For above is for C and below is for Ruston. I used uprob for oblast to trace functions internally. For example, the lex phase function. I showed lex phase function and pass phase function. Okay. So after measuring these bottlenecks, let's define some codes. At first, maybe iterating function may be a bottleneck. So I decided to reduce iterator method in Rust. I found this function named peak is very many times called on lexing process. So I changed the definition. This change leads to reduce whole usage of Rust string. String is internally a vector, so this occurs allocation. So I used UH instead. And then measure. The result seems to be not bad. But on the other case, when the target string is a bit longer, differences between Rust and C is still noticeable. So I decided to do next action, reducing realloc. I wrote new BCC code to count up realloc. Then very many times, found very many times code. So to reduce realloc, I try to allocate vectors memory in advance. So specify the vectors capacity using vec with capacity, and then measure it. But the effect seems to be limited, so to be continued. But small refinements are applied. This is, oh, thank you. This is a whole result, and Ruston is now took 0.05 seconds, and CJSON is like it's near to CJSON's performance. So lessons learned are first, existing tools are very useful, for example, perf. But to grasp detailed bottleneck, making simple BPF tool is effective. UProbe is an entry point to X-ray native programs performance, such as C, C++, and also Rust, maybe Zig. The most important point is just keep them in mind. Measure, reproduce, and measure. Okay, so conclusion is that BPF for observability gives strong power to us, but observability is hard way. But using Ruby, it's just a fun programming. So observability is your best friend. Enjoy and measure your program using Ruby. Thank you. I want to give some acknowledgements. RbBCC received Ruby Association grant in 2019. So thank you for Koichi Sasada to mentor me, Yosuke Matsumoto, Takao Shimayoshi, and Yoshiaki Kasahara to give me many advices. Thank you. I have uploaded sample codes. Share later.